Hello, year 13 doubles. So we're back to this old thing again, me doing online lessons with video via YouTube. Um, I want to make sure that on the timetable, and I've mentioned this in the classroom write-up, that on the timetable, all the lessons where I normally have year 13, please feel free to try and get in touch with me via Zoom or Skype if you come to any questions in any of the exercises. I just want to emphasize that. I can't emphasize that enough. I will be available in any of my year 13 slots on my timetable, which, as you can see on Google Classroom, is quite a few slots indeed. You can email me to check I'm going to be there first, by all means, but I should just be there sitting by my computer, and if I'm not talking to another student, I'll happily talk to you. Do get in touch, find the nasty questions, and let me know, because I want to still be offering that support. With the rest of it, though, it will be a case of you just watching these videos and then knuckling down for the exercises. And I know you're very hard workers, and so I know you're going to do that. Okay, anyway, on this first video, I'm going to show you a proof by induction with a matrix, which is the last topic in the chapter on proof by induction that we need to do. So I'm going to actually be running through question 5 from the textbook. That is here. Let's see if we can just zoom in on that. Let me just zoom in on that. I'm going to do this question here. I'm going to prove that result, and then I'm going to hence find an expression for the inverse of m to the power of n in terms of n. And it's a 10 marker, as you can see, so let's make sure we can do this. Now, the good news is this is probably the easiest proof by induction type to do out of the 3 types that we've covered yet. So far. Proof by induction with matrices is honestly easier than proof by induction with a series or proof by induction for divisibility. So let's go through it without further ado. The structure is exactly the same as before. You need a base case, and the base case is almost too obvious on some of these, but you still want to write it down because it's part of the argument. M to the power, well, clearly m to the power of 1 is 2051. Yeah, we're told that in the question. And according to our result, m to the power of 1 should be 2 to the power of 1, 5 times 2 to the power of 1 minus 1, and then 0 and 1, which naturally I'm just going to write equals 2501. And then I'm going to bore the examiner a bit more, saying, hence the result holds in the case where n equals 1. And that is the base case. Good. Okay, assumption step. Okay, assume true for n equals k. I wouldn't bother writing down base case and assumption step in the exam. Well, I'd probably put base case down, but I wouldn't write down assumption step. I'd just say assume true for n equals k. I.e., if m equals 2501, then m to the k equals 2 to the k, 5 times 2 to the k minus 1. Sorry, that k is really tiny there. 0 and 1. Cool. Okay, now the important and interesting part of the argument. I'm just going to move the screen down a little bit so we can do it. Proof by induction is a written argument. It is not about just coming out with a result. It's about convincing the examiner that this must be true. Okay, the inductive step. I would like you to... okay, so then for n equals k plus 1, we have... Now, we know what m to the k is, so I'm going to write m to the k plus 1. Well, that's the same as m to the k times by m to the power of 1, which is, of course, 2 to the k, because that's assumed to be true, 5 times 2 to the k minus 1, 0 and 1. I'm going to multiply that by 2, 5, 0, 1. Now, what am I hoping to obtain here? Well, I'm hoping to obtain this, but with k plus 1 substituted for k. So I'm hoping to obtain 2 to the power of k plus 1, 5 times 2 to the power of k plus 1 minus 1, and then a 0 and a 1. And I'm sure that's exactly what's going to happen. That's what I like about proof by induction. It's quite a snazzy argument. 2 to the k times 2 is 2 to the k plus 1. And then you've got this times by 0, and that's obviously 0. So we get exactly what we want in that first element. In the second element, we're going to be doing 5 times 2 to the k, and then we're going to be adding on to that 5 times 2 to the k plus 5 times 2 to the k minus 1 multiplied by 1. So that's just 5 times 2 to the k minus 1. So it ends up being pretty messy, the algebra in the elements, because obviously there's just 4 spaces here. 0 times 2 plus 1 times 0 is 0. And 0 times 5 plus 1 times 1 is 1. So just to make it clear with a bit of colour, that's my first element. This unwieldy beast is my second element. This is my third element in the matrix, and that's my fourth element. Now I've just got to tidy it up, really. So let's do a bit of tidying. Clearly I've got what I want in there, but it's really just that second element in question. 5 times 2 to the k plus 5 times 2 to the k. Well, I suppose you could say that's 10 times 2 to the k, but can you see that is 2 lots of 5 times 2 to the k? And this is where the answer is going to come in. And then we've also got a minus 5 on the end, and then 0 and 1. And can you see that that is the same as exactly what we're looking for? Basically, it is the result, because the powers of 2 we can add together, giving me 5 times 2 to the k plus 1 minus 1, just as we were hoping for. Yeah. And now we just need the inductive remarks. Now they don't really change. We can say, this is just a result with k plus 1 substituted for n. Hence, truth for n equals k implies truth for n equals k plus 1. I like saying it like that, because actually it's quite a quick way of writing it down. Truth for n equals k plus 1. And since it's true for 1, because you've got to bring in the base case, remember, and since it's true for n equals 1, it follows it's true for all n, which are members of the naturals. I think every time I do the inductive remarks, I put it in a slightly different way, so apologies for that. But I think it shows understanding, though, if you just don't memorize something, but actually just put it in a slightly different way each time. But anyway, it doesn't really matter. Now, part B, this is like the fun bit. It says, hence determine an expression for mn to the minus 1. Now this is the inverse matrix. Resist the temptation to start manipulating the powers or anything like that. It's asking for the inverse matrix. Well, the inverse matrix is simply, for a 2 by 2 anyway, we just need to do our determinant, which is 1 over, now let's just go back to the answer, well, the original thing we were trying to prove. It's up here, yeah? 1 over AD minus BC. And our AD there is 2 to the n, and our BC is 0. So it's going to be 1 over 2 to the n multiplied by, and then we just need to switch 2 of them around and change the signs on the other 2. So it's going to be 1 minus 5 and 0. I'll just write it down now. 1 minus 5 times 2 to the n minus 1. I suppose I could put that in the bracket and make it 1 minus 2 to the n, 0, and I've forgotten what the last term is. Is it 2 to the n? I believe it is. I'm just going to check that, but I believe That is the final answer. I'm just inverting a 2 by 2 matrix in the standard way. So these two swap over and the signs change on those two. And that should be the answer in the back. Good. So I hope you can see they're not too bad, actually. They seem pretty obvious which way they're going. Try the exercise 8C, questions 1, 2, 3, and 4. Because we've done 5, and then go on to the mixed exercise. Now, I don't mind which ones you choose to pick here. It might be an idea to do question 5 because they use that funny notation, which you might get asked in the exam, so get used to it. But I'd like you to do 8C quickly, 1, 2, 3, and 4A, and then I'd like you to complete the mixed exercise, as many as you can do, really, and we can do a little bit more on that tomorrow before we start the second book. Okay, thank you for listening, and yeah, best of luck, and please do get in touch on any of the lessons that I'm free via Zoom should you find any nasty questions in mixed exercise 8. Okay, thank you very much. Bye bye.